This is 8a.3.2. Example 2 will now introduce the inner product of two complex vectors. A and B are complex vectors, and this is the inner product of A and B, as well as calculating the norm of B of a complex vector. Now, this is the canonical representation of inner product for complex vector. So generically, we write it as A and B. They are Cn, complex vectors with n elements. These are anchor brackets. And to calculate it, we use this formula. It looks very much like the dot product, except that the second element, the B, must be complex conjugated. Notational wise, we use BH. BH represents the conjugate transpose of B, or sometimes called the Hermitian. This is the shorthand notation of this expression. Bi bar represents the ith element conjugated of B. Ai remains the same, so it's Ai times conjugate of Bi for all, and we multiply and we sum for all elements. This is the definition of A comma B, where A and B's are complex vectors, and this is the definition of the inner product. Let's have some example. A is these four elements: 1 plus j, 2 minus j, 3 minus j, 4 plus j. B is 1 j minus 1 minus j. So what is the conjugate of B? Same column vector, 1 is remain the same. The complex numbers are conjugated. Remember, if A plus B is Z, Z conjugate is A minus JB. That's all. So A plus JB becomes A minus JB. The real part remains the same. The imaginary part has the sign inverted. So this, can you see? Only the sign of the complex numbers is inverted. And what about BH? BH is conjugate. So we first perform conjugate, and when we transpose, a column vector becomes a row vector. So it's conjugate transpose. So BH looks like this. So what is BH? B is simply this vector multiplying by the original vector 1 plus j minus 1 minus j. So it is a 1 by 4 multiplying by a 4 by 1, and we'll get a scalar at the end. So never mind, let's proceed. What is inner product of A comma B? Well, we take each of these elements of A, put it here, and then we take the conjugate of elements of B. So I'll use a different color now. Green. 1 becomes here. J becomes minus J. Minus 1 becomes minus 1. And minus J becomes plus J. You work out this, and the answer is minus 4 plus 4J. You can also do it the other way around. You can write it as BHA. So it is BH is 1 minus J minus 1 and J. And A is 1 plus J, 2 minus J, 3 minus J, and 4 plus J. Remember, this is a 1 by 4 matrix. This is a 4 by 1 vector. The answer is 1 by 1, a scalar. And the scalar is minus 4 plus 4j. So when we multiply, or when we perform inner product of two complex vectors, typically out comes a complex number. So this is the inner product. Let's discuss what a norm is. Well, when we want to find a norm must be a non-negative real number. I should say non-negative. It can be 0 only when the vector B is the 0 vector. So norm of B is defined as the square root of the inner product of these two vectors, the same vector, B and B. I color this in red so that I want to show you that the second entry must be Hermitian or conjugate transpose before we multiply by b, taking the square root. So this is the definition of the inner product again. And this is how you calculate the norm of b. Okay, so why do we want the second entry, we call this the second entry, to be conjugate transpose? And the reason is that it must produce a real number, this guy inside it. So let's try to find the norm of b. Alright, we substitute what b is. So this is b. And we also can substitute each element conjugated, which is this guy. So we plug in this and this into this equation, and we out comes a real number, 4. So it's surprising, right? Now typically we multiply a complex vector by another complex vector. We assume that a complex number will come out. But because we're multiplying by the conjugate for each element, then only the real value comes out. Okay, so this is maybe the real reason why when we perform inner product, the second entry is conjugated. So the other thing that you have to take home with is that the elements of B, each of these elements here, have length 1. And because we have length 1, then out comes each of these elements, when we multiplying by its conjugate, will still have length 1. So it's 1 plus 1 plus 1 plus 1. 4 times, because the length of this vector is 4. So it's square root of 4, and actually square root of n, where n represents this is the 4 numbers. But this only happens because the elements of B has length 1 for each of these elements. Okay, so with that, we're going to continue to discuss about the projection of V onto B, and you'll realize that we need to introduce this operation, V inner product with B hat and B hat. Alright, so with that, I'll see you in the next lecture.